Welcome to Learning Unit 8, Principles of Solidification. In this module, we will be learning about the solidification of solids from the molten state. This is a very important thing to understand, as the forming metal objects through pouring liquid metals into a mold is a very important process. Casting is of liquid metals into a mold is an ancient technology, and humans have been known to be doing it for at least 5,000 years. The oldest known casting is a copper frog, shown here, that dates back to 3200 BC and from the Mesopotamia area. What happens when a liquid solidifies? In a liquid, what will happen is that atoms will form clusters. Some of these clusters will be too small to be stable and dissolve back into the melt. Other clusters will reach a critical size, and such they will form nuclei. The nuclei are able to grow and form crystals. The crystals will eventually impinge upon one another, and when the temperature falls, the material will solidify into a polycrystalline solid. The formation of embryos and the development into nuclei can be understood in terms of thermodynamics. Free energy is a concept used in chemistry and material science and other fields. A system will spontaneously change in such a way as to reduce its free energy. A system can contain free energy for various reasons. For instance, let's consider a potential nuclei, or an embryo, which consists of a spherical solidified shape within the liquid. It has energy associated with it due to its state, it being solid, and the other state that it's in equilibrium with is a liquid. The solid forms because chemically the free energy content of the solid is less than the liquid. So that is driving the solidification process. As the free energy of the solid is proportional to its volume, and volume increases as r cubed, the reduction in energy of the system as the embryo increases in size, this axis representing the radius of the particle, will reduce as a cube function. So that's what the green line represents. It represents the reduction in energy due to the growth of the embryo. However, as the solid embryo grows, the surface area between it and the liquid is also increasing. This is an energy cost, as a surface contains energy. The surface energy grows according to the area of the sphere multiplied by the surface energy per unit area. And so the surface energy grows as the power r squared. We find that for nuclei that are smaller than a certain radius, they are unstable because it is not energetically favorable. They contain more energy than the liquid itself. That is because they are so small, the increase in surface area is not offset by the energy reduction by the formation of the solid. However, at a certain critical radius, the total free energy maximizes, and below that, increasing the radius of the particle reduces the free energy of the nucleus. So the idea here is that there is a competition between the volume of the solidified object and the surface area, and that once the nuclei reaches a certain radius, it is stable and may continue to grow, as by doing so a reduction in free energy is achieved. Nucleation occurs through the random creation of clusters, and this can occur uniformly in the material. When this happens uniformly, this is known as homogeneous nucleation. More likely is heterogeneous nucleation. Heterogeneous nucleation is nucleation that occurs on impurities, for instance, or on the surface of the mold. Because the solid-liquid interface is not as large for a nucleus forming on an impurity, the total free energy of a nucleus is less for heterogeneous nucleation than homogeneous, and so it will occur sooner. The rate of nucleation is again driven by two competing factors. With increasing temperature, there is increasing mobility of the atoms, and so the growth rate increases with temperature. However, the difference in free energy between a solid and a liquid is higher as the temperature is reduced, and hence the nucleation rate peaks at temperatures lower than the melting point. The difference in temperature between the temperature at which the liquid actually starts to solidify and the melting point is known as the undercooling. Most melts require a degree of undercooling in order to freeze. The concept of undercooling is important, and I have written it as an equation here. The amount of undercooling is equal to the melting temperature minus the temperature of the liquid at the point of solidification. The undercooling has a large effect on the mechanism and the morphology of the growth of the solid. When undercooling is low and the temperature difference between the liquid and the solid is small, and the growth rate is small, the temperature of the liquid is slightly higher than that of the solid. And heat conduction, the latent heat required to be conducted away as the liquid turns into a solid, occurs through the solid itself. This means that any protuberances on the interface between the solid and liquid die away, and we get a planar growth, a smooth, steady boundary that moves across into the liquid. However, such a plane is quite unstable, and with increasing undercooling and increasing growth rate, the growth can become cellular. Here we see growth of a number of crystals in a direction, and crystals don't grow at equal speeds in all crystallographic directions, and there will be a preferred direction in which the speed is more rapid. With even larger undercooling, the temperature of the liquid is cooler than that of the solid. This means that solidification of the solid is maximized by maximal contact area with the liquid, and that favors a tree-like structure. And the Greek for tree is dendron, and this morphology is called a dendritic growth. I will show you a video taken under a scanning electron microscope of the propagation of a planar growth front, which then turns into a cellular growth. Here we see the planar growth front moving towards the left. As the temperature reduces, it becomes unstable, and we see a cellular growth front forming. This is the computer animation of the growth of dendrites. From the three-dimensional animation, we can see how dendritic growth occurs along certain crystallographic directions. Here is a stunning photograph taken under a scanning electron microscope of some actual dendrites that grew in a cobalt samarium copper alloy. This is an optical micrograph of a section of a sample showing a two-dimensional section of dendrites. Here we can see the main arm, and then coming off the main arm are what are called secondary arms. The distance between the secondary arms plays an important role in determining the mechanical characteristics of the material. The spacing of the secondary arms, shown here in this diagram, is called the secondary dendrite arm spacing, abbreviated to SDAS. It is a function of the material properties K and M, but also a function of the total solidification time raised to the power m. Ts represents the total solidification time from when the melt is poured to when it finally solidifies. In this diagram, we can see how the mechanical properties of the material are influenced by the secondary dendrite arm spacing. Tensile strength is higher for smaller dendrite arm spacings, as is elongation. The total solidification time is determined by the mold geometry. According to this relationship known as Chvorinov's rule. The total solidification time, which is the time from when the melt is poured to when it finally solidifies, is equal to B, known as the mold constant, multiplied by the ratio of the volume to the area of the mold raised to the power n, where n is a constant for the mold material. This equation can be used to design parts of the mold, and also to determine if the total solidification time will result in the required microstructure. An issue with casting is that the volume occupied by the solidified liquid is less than that occupied by the liquid itself. This reduction in volume is called solidification shrinkage, and can be a serious issue in a number of metals that are commonly used for engineering applications, such as aluminum. We see that aluminum has a volume change of 7% upon cooling. Some materials, such as bismuth, actually expand on cooling, and this can help to fill the mold and produce features, fine features in the mold in a reliable fashion. Where there is significant shrinkage results in some common defects in the mold. Consider if a cylindrical mold is filled with a liquid metal. The outside, the liquid in contact with the mold initially freezes. As the material closer to the center of the cylinder freezes, we see that we are running out of liquid, because the solid occupies less volume, less volume than the liquid. This results in a void within the mold. A void with this characteristic shape is called a pipe. Its volume represents the shrinkage volume of the melt. In some cases, the voids get entrained within the mold itself, resulting in internal voids. Here we see a computer simulation of a pipe compared with the actual pipe seen under experiment. In order to avoid the formation of internal or external cavities due to shrinkage, a riser or a feeder is attached to the casting in order to feed the casting while it is solidifying. The riser must then be removed in order to result in a functional object. Although this results in extra material being required for the casting, it results in a casting that is free of defects due to shrinkage. The riser must be designed such that it solidifies much after the main mold, so that liquid may be maintained within it for a sufficient length of time to feed the main casting. Graphs of the temperature of the liquid as a function of time are called cooling curves. Here we see a section of a cooling curve. We see that initially the liquid cools below the melting point. This is called undercooling. Undercooling is required for the sufficient nucleation rate to be reached. Once nucleation or solidification occurs, the latent heat released from the solidification reaction raises the temperature of the melt back up to the melting point of the material. Then the graph plateaus, because the heat released from the solidifying liquid is equal to the rate at which heat is being lost from the liquid and the solidifying material itself, or being lost from the mold. This happens, the plateau continues until all the liquid solidifies, at which case the heat being lost by the mold to the environment is not being replaced from the latent heat being released. On a larger scale, here in a well-inoculated melt which does not have significant undercooling, we see this graph. This graph shows us some various interesting features, or features of interest. Number one is the superheat. The superheat is the temperature difference between the pouring temperature and the melting temperature of the material. The melt may be superheated to ensure that it doesn't solidify before it has completely filled the mold, and also to ensure that it remains to reduce viscosity, for instance. Also marked on here is the total solidification time, which is the time from when the melt is poured to when all of the melt liquid solidifies. The local solidification time is the time between when the material starts to solidify and when it stops solidifying. When the melt is poured into the mold surface is cooler and hence nucleation will occur in that region. When this happens, the nucleation at the surface causes the formation of randomly orientated grains, and in the thermal gradient certain crystallographic directions will be picked out and grow into what are called columnar grains. These will extend until the liquid in the middle cools to such an extent that additional nucleation occurs and we get equiaxed grains or randomly orientated grains. This can be seen in this cast sample here. You can see the columnar grains in this casting. Another issue that can occur with dendritic growth of the crystals is that the dendrites can themselves trap areas in which liquid cannot be fed, and this results in interdendritic shrinkage. And this can be reduced by having smaller, more evenly spaced dendrite arms. Another thing that causes porosity is gas porosity. Gas porosity occurs when gases that are dissolved in the melt, the gases come out of the melt because the solubility is less in that lower temperatures and in the solid than in the liquid state. So the gas comes out, and if it's not allowed to escape, will form bubbles and pores within the melt. Gas porosity can be reduced by casting in a vacuum or bubbling inert or reactive gases through the melt to remove them. I've listed a number of different types of casting processes here with some videos to explain what they are, and I would encourage you to go and watch them. An interesting modification of the casting process is to create thermal gradients, deliberately create thermal gradients in the mold in order to cause directional solidification. And the reason for doing this is to produce crystals with a preferred or with a certain orientation in the material. Here we see a simulation of the casting of a polycrystalline columnar grain gas turbine blade. A thermal gradient is created within the mold, such that crystal nucleation occurs at the bottom, and then we get columnar grains. We see the grains indicated by different colors, which then grow up into the casting. And there's an animation here which I will show you, which shows how the columnar grains grow. One step a further advance of this is to actually select, using a tube such as this, to select just one crystal from the columnar grains that are growing in the base that will seed the solidification of the rest of the turbine blade to result in a single crystal turbine blade. And there's a simulation of how that occurs at the link shown. We can see here the columnar grains are growing, and then one is picked out, and then a single grain goes on to solidify the rest of the turbine. Single crystals may be grown from the melt using very specialized techniques such as the Chvorinov process or a related technique called the Brigham process. You can see here a video of how silicon for microelectronic circuits is grown from the melt. And that's it for this module. Thank you very much.